All right, everybody, are you there? Now, students, are you able to see me or my, let me see. Oh, you're able to see my document camera. Okay, now students, are you able to see my screen?
Yes.
No.
No?
Oh, your screen? No.
Right now we see the laptop or like the camera.
The laptop.
Now we see the screen.
Oh, great. Okay. All right, so let's do this. Okay, now I want to know if I'm able to give you some quiz. Are you ready for the quiz, or do you want to ask any question before we get started?
The quiz is on the spinach construction, right? Is it like on the lab process, or is it on the
Oh, it is always the pre-lab quiz about the experiment of the day.
Okay, thank you.
Okay, I mean the entire experiment of spinach extraction. Yeah.
So are we going to be asked? Sorry, you go ahead.
Go ahead. Did you have a question about?
Yeah. I was just going to ask, are we like expected, are we going to be quizzed on like anything from the Making Connections book today or in general? Or is it just from the lab?
It is about the experiment that you're scheduled to do. Okay, so it will be on this procedure coming from the lab manual plus the theory behind it.
Okay, all right, thank you.
Okay, but usually it's, something that you read, you get it. There is really not much thinking involved. So as long as you do your reading assignment, you should be okay. Okay?
I have a question.
Yeah.
Yes. So for the chromatography, it says that the stationary phase is always more polar than the mobile phase. Can you explain that a little bit?
Okay. All right. That is a really good question. Okay. Let me put you on my document camera. How about that? Okay. I need to draw something now. Okay. Are you able to see my table?
Yeah.
This is my tablecloth. Okay. Let me. Actually, I lecture from kitchen, so I'm closest to water. And this is my lunch table. All right. So let me move this a little bit. Okay. Remember in TLC, you learned TLC before, have you? Okay. And so TLC plate goes like this. There is a white coating, am I right?
Mm-hmm.
The white coating. Okay, so the white coating is usually like silica gel or some ionic compound we make into paste and we coat it on the plastic backing, okay? So this is usually polar substance, okay? The coating is always polar substance, okay? So when you put your compound on it, on the baseline, okay, so this is compound A, B, C. Remember you did it in the A, remember? 223A, yeah. Okay, so compound X, Y, Z, for example, okay? And you put this, your dot compound X, dot compound Y, compound Z. Okay, and at the beginning of the experiment, when you create the 3 dots, where the 3 dots actually stay in place, it is not moving at all, right? Remember that, right? Okay, then you put the TLC plate into TLC tank where you see this solvent, eluent, right? Going up, am I right? And this solvent molecules will come to this baseline and dissolve this compound Z, then start moving up together. Am I right? Okay, this is what you did when you run the TLC. Okay, so how come at the beginning of the experiment, the XYZ dots stay in place? Okay, number one, it is solid. Okay, solid substance in here and in a very strong polar background. Oh, okay, actually a deposit in place. So this background being polar is able to keep the compound you dot on the baseline. Am I right? Okay. And so you really need a good attraction in order to make that dot stay in place, or else if it is not solid, then the liquid can move around. Am I right?
Yeah, that makes sense.
For this reason, yeah, for this reason, the background needs to be polar. Okay?
Okay,
All right.
thank you.
And eluent, you can change the polarity. Okay? Okay. Are we ready to go? Now, students, okay, let me tell you this. I will stop share and then we'll go back to the question. Okay, now TLs, oh no, we're not doing that. We're doing pre-lab quiz. Okay, now students, before we get started, okay, now this is the quiz. And I give you the choice of, you can download this file with the quiz question. Okay, and originally I also create answer sheet. Now I realize I don't really need it, okay? I realize if you're able to go into Dropbox, go to Dropbox, and you know, you click this, you're taking it on Wednesday. And then if you do submission, you'll be submitting your answer, okay? Then you can attach a file first, then you can write underneath. Okay, I will ask someone from my class to volunteer, if you have done this before, from your Dropbox, submit the answer by typing in the answer into Dropbox. Can you raise your hand and let me screen share with you? Because my instructor page is not the same as the student page, okay? It doesn't display the same thing. So I will have to rely on students here, volunteer to share screen from your end, and we can write answer directly into the Dropbox. Are you with me? Hello?
Yeah. I can share my screen, but I'm kind of confused as to how we're submitting.
Oh, okay. Let me screen share with you, then you understand, okay? I need to find my Zoom bar. Where's the Zoom bar? Hey, what's going on here? Okay, I will be able to find my Zoom bar better this way. It's right here, okay? My Zoom bar. Okay, I will, from security icon, I will ask you to screen share, okay? And I will ask a volunteer. You can actually screen share now from your end when I stop sharing first. Okay, resume. All right. All right, now students. Today you will be doing extraction of the pigments from spinach first. Hey, why is this moving up and down? I don't understand. Okay. It's probably, no one's moving this camera. But anyway, it's probably, you never know,
It
earthquake.
might just be auto-focusing, Professor.
It is, huh? Okay. All right. So in spinach, there are so many different groups of pigments. Okay? Okay, xanthophil. Oh my goodness, what a fancy name. And keratin, and so very minor difference there. Then you see chlorophyll and then phyophyton. Okay, oh whatever. Okay, now tell me between this many pigment groups, which group you think is most polar? Which one is most polar? You have the book also, and I want you to take a look.
Is it xanthophyll?
Which one is most polar? What do you think? Now someone's offering an answer, and you said this one's most polar?
Yeah.
And if we compare that with chlorophyll family or phyophyton, which one's more polar? What do you think? Between
The fear of fighting.
I think it's phyophyton.
the most polar one, you think between these two,
Is the one on the right, phyophyton.
you think this is more polar, right?
Yes.
Okay, let's see if this is the case in the experiment, okay? I can tell you right here, you have magnesium, and most likely it is a +2 charge, right? Magnesium is a +2 charge. It's not metal, 0 charge, okay? Magnesium right here, they should be writing a plus, it's an ionic compound, basically. Is nitrogen electron withdrawing? Yes or no? Is oxygen
Yes.
electron withdrawing? Tell me on the periodic table, which element has the highest electron negativity?
Fluorine?
Fluorine, F, right? Then what comes next? What comes next after fluorine? Someone said this is the most electron withdrawing. What comes next?
Oxygen?
Then
Nitrogen?
FON. Now, who gave me this answer? Fluorine, oxygen, and nitrogen. I want to give you a bonus point. Give me your name.
Nathan?
Okay, let me write your name down. So this, you're in section 2. Last name is,
Vu?
thank you. I'll give you 1 point, Nathan. Excellent answer, okay? Because I have electronegative elements of oxygen and the nitrogen at the same time in this molecule. So between these two, if I tell you this is probably a little bit ionic right here, I have a feeling it's probably chlorophyll, the green compound. This is actually green color, okay? And phyophyton is probably in between. So you may say, Ms. Jean, how do I know the color? I don't know. I just go by the book, okay? So if you have the book right here on page 24, okay? Okay, so it is telling you, oh, phyophyton is actually in between chlorophyll and the keratin, okay? All right, so go back to keratin again. Is keratin polar or non-polar? Is keratin right here, keratin family, are they polar or non-polar?
Non-polar.
Non-polar. Why is that? Can you tell me why?
Don't have any polar molecules as any of the functional groups. A lot of it's just carbons and hydrogens. And then,
Exactly. Now, who gave me that answer? Hello? Who gave me that answer?
Simon.
Simon Chow, thank you. You get 1 point, okay? Thank you.
Thank you. 。 you. 。 。 。 。 。 。 。 。 。 。 . 。 。 . 。 。 . 。 . 。 . 。 。 . 。 。 . 。 。 . 。 . 。 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 .
Yes, okay, because carbon-hydrogen bond is not polar at all. Carbon-carbon bond, of course, this is covalent bond, right? So one more time, between keratin, okay, now keratin is this molecule. I don't see oxygen, okay? I don't see nitrogen, okay? All the electronegative elements are not there, so I know, okay, this is more polar because you see a whole bunch of oxygen, right? Oxygen, okay? And then between the two, I said, this is probably ionic, okay? So, oh my goodness, this is more polar, okay? All right, so why do I have to emphasize this? Because the column chromatography, or TLC, if you hear the word chromatography, it is all based on the isolation of compound because the difference of polarity. And you remember in the TLC experiment, someone just asked me about this backing of TLC plate. That has to be polar, okay? And I talked about that already, okay? So the backing itself is polar. Okay, and you know, based on the difference between X, Y, Z, if there are different in polarity, then mobility on the plate will be different, okay? We'll come to that later, okay? I want to talk about only the column today. Okay, I think I gave you a question at the beginning in the quiz. I asked you what's in there in the column today. What's inside of column today?
Alumina?
The alumina. Someone says alumina. Okay, and is alumina polar or non-polar?
Polar.
All right. All right, I want to see who gave me the answer. Who gave me the answer? This is alumina and it's polar. Who said that? I want to give you points.
Nathan again.
Nathan again. Oh my goodness, Nathan, you really study hard. I see potential A student right here, okay? You have great potential. So this is a polar we call adsorbent. Am I right? Adsorbent. This is particles that's capable of attracting polar molecules. Okay, so if I give you mixture of two compounds, okay, coming down, okay, and I give you a mixture of, how about the keratin family, okay, keratin. One more time, is keratin polar or non-polar?
Non-polar.
Non-polar.
This is non-polar, okay? This is non-polar. And the green chlorophyll, is that polar or non-polar?
Polar.
This is polar. I just asked you to look at the structure of the two molecules, right? All right, so if I have mixture of the two, okay, this mixture is coming, okay, and coming down the column. And I will have to pre-moisten. This is the question I asked you already, am I right? You will add hexane. You will add hexane to moisten the column, okay? You moisten the column, the alumina. You moisten the adsorbent, saturated with the solvent that is non-polar. Then you can charge this two, the mixture of the two, into the column. And then, because like dissolve like, because, follow me, the polar adsorbent will pick up the polar chlorophyll molecule. adhere strongly, tightly. They attract each other strongly. Why is that? It is just like small magnet attract the other small magnet. Am I right? And this nonpolar substance is just no attraction at all to the alumina because, hey, you polar and I'm not polar. So we have no attraction in between. Am I right? You understand that, right? That is the principle called like dissolves like. Am I right? Birds of a feather flock together. The polar substance will hang out with polar substance better and dissolve each other. And for this reason, water and alcohol, for example, are they gonna like each other? Hello? Do they dissolve each other?
Yes.
Because of hydrogen bonding, all right? They both are polar, that's why, okay? And water and hexane, are they gonna dissolve each other?
No.
No, not at all. Hexane is non-polar, right? 6 carbon and there's only hydrogen here around the carbon. Each bond is non-polar here. So water and hexane would not dissolve each other. Okay? So try to understand like dissolve like attracts like. Okay? You will find adsorbent and the chlorophyll attract each other, and you will see chlorophyll strongly held down by the alumina particle at the top. How about keratin? Keratin will not be much absorbed by the particle of alumina. It will just go through much quicker and elute out of the column before chlorophyll will start moving, okay? We will see that in a minute. I'll show you the video. To see is to believe, okay? All right. Now, ladies and gentlemen, do me a favor. Can you open up the procedure? Can you open up a procedure, hello? That procedure is actually from my course package, okay? Can you cut down the noise, please? Okay, I'm lecturing. Okay, hello. Do you have the packet with you, hello?
Yeah.
Yes.
Can you open the course packet and show me the page? Now, students, I want you to read the procedure carefully, okay? We made the change against the lab manual because that's the only way to make the experiment work. It does not work according to the procedure written in the lab manual. That's why I have to make the change, okay? All right, so right here. Looking at the same page? Okay. In a centrifuge tube, okay. And we will start the experiment by transferring the spinach puree, add acetone, okay. And I want all of you read the procedure with this page open next to you when I play the video. Are you ready? Are you ready? Okay.
Yes.
Good, thank you. And let me play the video. Okay, now students, try to interact with me, okay? Because students are able to pick up some points. Oh my goodness, I didn't really catch your chat, okay? I'm sorry, but the students with the microphone will, you know, will have the advantage. Okay, let me do this. I need to go back to my the video link, okay? And share screen. Okay, are you there? Okay, ready? All right, let's see whether this is gonna show you the result we wanted, okay? All right, transfer the spinach extract to the centrifuge tube. Oh, the TA is moving the puree. So just want to give you some idea, okay? The spinach, we got it from a supermarket, okay? And then we add some salt, we add a little bit sugar, and then we add a little bit acetone, okay? And then stir and put it in juicer, whatever, break it apart. And this is what's in the beaker. We made the puree ourselves, okay? And see how pasty it is? Oh, okay, now the pipette is just too narrow at the tip to get the puree up. And actually, there's a way to do it quicker. We can use the pipette with the, much bigger diameter of the tip. But on the day we video it, we didn't have that as an option. Okay, so finally we got the puree transfer in. So next is to add acetone to the centrifuge tube. Acetone, acetone. One more time, acetone. This is not the acetone coming from the wash station. It is actually a real reagent grade acetone. Okay, we add acetone to the puree. And we cap it. And shake well. You want to shake it. Okay, to the puree, you add acetone and shake it. Tell me, what is the purpose?
Mix it really well.
I'm sorry?
To mix it really well.
It is only to mix, just to make it beautiful and well mixed.
Also to dry the green solution.
How do you dry something by adding acetone? Tell me. Acetone is not a drying agent. Am I right? So it's something else. Why do we want to shake? Shake and shake and shake. After shaking, tell me, what is the purpose? And actually, in the procedure written in my course packet, I even said, hey, you add acetone, not hexane. You stir with a glass rod. You cap and shake for 1 minute. Hey, why do I want to do that?
Is it to separate the organic layer?
Right now, there is only one layer. Oh, yeah. Let me tell you, young lady, acetone and water actually mutually dissolve each other. Okay? You're not too far, but I need to correct you about the concept, okay? So please give me 1 minute. Are you able to see my board? Whiteboard?
Yes.
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 Is this the acetone? Is this acetone? This is acetone, hello? That is
Yes.
acetone, okay? Now, is this polar or non-polar?
Polar.
That's right. Okay, so does it like water?
Yes.
Just look at this, right? Is this hydrogen bonding? Yeah.
Yeah.
This is hydrogen bonding. Yeah. So let me tell you, acetone and water actually dissolve each other. We call miscible, right? You learned this word, have you?
Yeah.
Miscible. Okay. So let me tell you, acetone and water. Okay. And you grow spinach in the field. Do you water the plant every day?
Yeah.
Okay. So the spinach itself comes with a lot of water already, believe me. Okay. So how do I extract the pigments inside of spinach? Okay, now I have a spinach leaf right here. Let me use a green color. This is my spinach leaf, okay? Okay. Does it have a lot of water? Does it have a lot of water?
Yes.
Does it have a lot of pigments already here? Yes.
Yes.
So what is the purpose of adding acetone? Hello?
To make it greener, for the organic layer to go up.
You want, let me tell you, students, do you want all the pigments out of the fiber? And we call this extraction, right? Have you learned this word called extraction?
Yeah.
Extraction. Like when you drink tea. Okay, you got the tea leaves or you get powder tea, doesn't matter. Particle form, doesn't matter. Do you want the tea in the water? You stir it, you want all the goodies out, you want the aroma, you want the flavor molecules out of the tea. What do you do to get all the goodies out of the tea? How do you do it? You stir, right? You extract, right? Am I right? This is called extraction. Okay, you add acetone in order for the chlorophyll and all the pigments swim into acetone. Okay, you're adding acetone in order to extract the pigments out of the leaves, or else, you know, you're not fully utilizing the raw material. Are y'all with me? Hello? Do you get it?
Yes.
I think
Okay.
so.
All right. So let's do video again. Okay. All right. And I truly like this, video recording right here. It's really great. Okay. Result after shaking, just like tea bag. Ooh, ooh. You want the water into the tea leaves, okay? And you shake and shake so all the goodies will dissolve in that solvent, okay? Okay, after shaking, my goodness, a lot of green juice, okay? And then what this TA trying to do, weigh the mass of the tube to counterbalance against another groups of the similar mass. In other words, when you use a centrifuge machine, you have to make sure this is in the same weight. So the centrifuge machine does not lose balance, okay? You don't want to spin it in, with different mass. Okay, and load the centrifuge and the sample, okay? And it starts spinning for 1 good minute, okay? You know, I have to stop right here, okay? It seems to me this is going back and forth. This is not right. I mean, it's just a wrong, it appeared to be going clockwise and then counterclockwise, back and forth. It wasn't the case. It just appeared to be, okay? You know, just a reflection of light, okay? Okay, about 1 minute. Now, can someone tell me What is the purpose of centrifuging? Bonus point.
The purpose of centrifuging is to kind of form a pellet, or when you're centrifuging and spinning it around, for the contents to settle at the bottom of the tube and separate the layers.
Hold on, because let me read their suggestion here. Study group. Okay, very good. All right. So someone said you want to separate the groups according to what?
Density or size.
The density and size. Did you say size? The centrifuge work according to the principle of density. Those with higher density will stick to the, tell me, bottom or the top?
Bottom.
At the bottom. Very good. Okay? Okay, so centrifuge will help you precipitate any solid at the bottom of the tube. Am I right? Okay? And that way you can actually separate the puree fiber away from the pigment solution. Okay, you will see that right away. Okay, you will see that right away. When you take it out, look at that. Look at that. Do you see? Do you see the pulp? Okay, is actually sticking at the bottom. There will be some at the bottom. Okay, and some will probably stick to the side when you know, when you have a lot, when you have so much, and if you spin long enough, let me tell you, all these pulp will go down. Okay, so do you see this green, very deep green solution right here? This is a lot of the pigments dissolve in the solution. Now tell me once again, can someone tell me what is the solvent here? What is the solvent here in the solution? What solvent is this? Hello?
Acetone?
Acetone, thank you. It's acetone, okay? Because you add acetone. There may be some residue water coming from the spinach itself, okay? All right, majority of it is acetone. And your pigments dissolve in there, okay? Okay. Okay, now the TA is moving the green juice into another centrifuge tube, okay? And he did the same with another tube. And then he will add small scoops of drying agent and shake well until dry. All right. What is the purpose here? It tells you, I want to dry it. I want to dry it. Why do we have to dry it? Can someone give me a reason why we want it dry? This is probably hard. This is quite hard, but if you are able to figure out, I will give you a bonus point. Why?
Is it to remove residual water?
Yes, that is the definition of dry. But why do we have to dry it before we?
Because when we're doing the column, it works on the principle like polarity. So our alumina is like polar. So if we have excess water in the mixture that we're trying to like put through the column, then it's gonna like mess with the results a little bit.
Exactly. Is this Simon Chow?
Yeah.
Simon, I'll give you one more point, okay? Now, students, it's actually not too difficult to come up with a great answer as long as you apply yourself, okay? Let me show you the column again. Didn't I show you the column at the beginning of the lecture, okay? Let me show you the column one more time. I really like students who are able to figure out the answer on your own. This is amazing. This is a very, very aggressive group, okay? I like the students who are able to answer such a question. It's not easy, okay? Now, students, can I give you some warning right here? Water is killer to column. Water is a killer to the column. Do you read the message? Do you understand? Water is a killer to the column. Alumina is superpolar, okay? If you want to destroy the column and make it dysfunction, malfunction, or not function, or not active at all, just block all the particles with water, and this column is dead. Do you hear me? Okay? Alumina itself is polar, just like NaCl, okay? Is sodium chloride, is it polar? Is it ionic? It is ionic. Does it like water? Yes, okay? And so if sodium chloride is solvated by water molecules, does it function as ionic particle anymore? It doesn't. It's a dissolve. Okay? Alumina, if you cover it, all the particles, okay, particles of alumina, and if the surface is blocked by water, it does not separate the mixture anymore. It will die. It does not function. It does not absorb other things because it is all covered by water. Do you hear me? Okay? Important common sense. Okay? And let me tell you, for this reason, for us to provide you alumina, good alumina particles for use, we have to bake alumina sometimes for a couple of days in the oven before use. If the alumina particles form clumps during storage, then you have to return that back to me. Miss Jean, this alumina is bad. You will have to bake it, remove all the moisture, remove all the water, or else I cannot use it as a adsorbent in the column. Understand? This is important common sense, okay? All right, let me go back and I can continue play the video, okay? All right. All right, so what drying agent was used in this case? Hello? Hey, what was the drying agent?
Anhydrous sodium sulfate.
All right, who said that? Finn?
Yes, Amanda, Finn.
I'll give you 1 point. Okay.
Thank you.
Thank you for responding back. Okay? Yes, we add drying agent to get rid of the moisture. Okay, we dry the solution so that moisture does not kill the column, right? Okay, and so look at this. Are you following my arrows right here? What is this?
Yes.
What do you see in here? What is this? What is that? What is that white thing? A little bit white. What is that? What is that solid? It's probably solid, right? What is that? Hey, students, are you sleeping or what?
No, just trying to figure out the answer.
What did you do here? Hey, it was just a minute ago. So what's on the bottom?
Yeah, the drying agent, yeah.
Yes, thank you. All right. All right. All right. Next, we'll have to prepare the column. Remember, that was the column I gave you the drawing. Okay, that was a column for the column chromatography. Now we are talking about filter column. This column is not the same column as the one we run for pigment separation. Okay, this is a filter column, although we use the pipette, okay, as a Mickey Mouse column. Okay, we actually use a cotton ball, and we want that green juice going through this cotton ball in order to get rid of the pulp. Any particles you don't want to contaminate, or you don't want any solid introduced into the chromatography column. Okay, you don't want to block the side. Okay, you don't want the top layer filled with a lot of solid. Okay, so this is a must do. Okay, any solution that will enter the column, you have to filter it first. Okay, so this is the cotton ball that goes in. Okay, and we set it up. And we want to receive the green solution. Okay, all right. Tell me, what is the purpose again for doing this step?
To get rid of the pulp.
To get rid of the pulp that may be suspending in the solution, or you want the solution free of the particles, right, from the drying agent, right? Okay, very good. See? Okay, now filter any pulp, any particles will be kept out. And so it comes down to, yeah, this vial. Transfer the dry extract through the filter, all right? And then we want to do solvent removal. This is all in my procedure, okay? This is all in my procedure. I may ask you the same question in the final exam, okay? You're doing this for a purpose. You want to get rid of the acetone. Remember, it was acetone inside the vial, right? Hello? The solvent that was in the green solution, it's acetone only, okay? All right, and we try to do this. Solvent removal, you can put the air stream, gentle air stream, and you see this air purging right here, a little bit purging at the surface. Gentle air, okay? So what is the purpose? Bonus point opportunity. Why do
We're trying to please finish.
I want to know why we want to get rid of the solvent here. Why do we want acetone completely evaporated? Now, can someone offer me potential answers? Which potential? What is the reason?
Is it for the same reason we wanted the water out, because it would interfere with our results since it's also polar?
Natalie, you're not too far from the real answer, but the thing is, remember, by adding the drying agent, it is moisture free. We are trying to get rid of the solvent, which is acetone in this case. Am I right? Right?
Yes.
Yes. Okay, Natalie, think a little bit further. You're on the right track, okay? I just want you to think a little bit further. We don't want acetone at all. We want something else, okay? All right, so we'll come back to this drying evaporation process later, okay? I want all of you, please. Okay, can you take a look at the procedure written in the course packet? Can someone help me read from the middle part of the paragraph? Okay.
What are we reading?
Reading that course packet, day 1, that paragraph. We finish filter column, right?
Yes.
Then help me read the sentence.
While waiting, prepare a filter column with a clean pasture pipette and cotton plug. Transfer the dried green solution into the filter column to remove the drying agents.
Yes.
Save the,
Yes. Save, then save the filtrate. Keep going.
save the filtrate in a clean vial.
Okay, this is what we do in here, right in front of your face. This is already displayed in front of your face. You save the filtrate, am I right? In a clean vial, and you allow air to gently blow over the solution until all solvent has evaporated. So what's that again? What solvent has evaporated? Everybody, hello?
Acetone.
Yeah.
Acetone evaporated. And then next, someone help me read the next sentence. Is Simon here?
Yeah. Save the filtrate in a clean vial. Allow air to gently blow over the solution until all solvent is evaporated. Add a minimal amount of hexane to redissolve.
Stop right here. Add a minimum amount of hexane to redissolve. Redissolve what? Redissolve the pigment here. Am I right? Are you following my hand?
Yes.
Right here in that vial, acetone's gone. You see pigment precipitate right here. Okay? And you want to redissolve it in hexane. Use only minimum amount of hexane to redissolve it. Make it a solution again. I want somebody to tell me what is the purpose. Once again, there is a hint, there is a hint. Tell me, is acetone polar or nonpolar?
Polar?
Polar. The polar solvent evaporated, and you want to introduce a small amount of hexane redissolve. Is hexane nonpolar or polar?
Non-polar?
Okay. Now tell me, why do we want this pigment back to hexane solution?
It's because when you're doing the column chromatography, you're supposed to use a less polar solvent first.
You
to extract
want
the...
exactly. Nathan, excellent answer. You get 3 points already. Oh my goodness. I want you to keep going, okay? This is how my students, A students, I'm talking about semester grade, A students, they're able to do well because they constantly understand the purpose of each single step they're doing, okay? Those students definitely deserve bonus point. And at the end of semester, they deserve a good promotion. And for your information, in my class, it is not unusual. Students get 10 or 12 points from the whole semester. Okay, it is really helpful. Okay, now the rest of you, hello, you know the answer, but you are shy. The problem is you're shy. Okay, now, okay, from now on, I want all of you participate in the discussion. Anything I discuss right here is important to you, okay? Because you really need to know how to run column, okay? You want to precondition the column using hexane later. The column itself with alumina inside, you want to reset the column at 0 polarity first, okay? If that's the case, you want the entrance, you want the solution entering the column at the same polarity. That's why this two, okay, the two same polarity will not get into fight later. Understand? Okay? Okay, so it evaporate. Guess what? This whole process takes a long time. Usually 10, 15 minutes, okay? Oh, it's only pigment residue. Pigment residue at the end only, all right? All right, another pipette, cotton, ring stand, okay? add alumina. Okay, so what column do you call this now? It is the real chromatography column. Am I right? Hello, are you there? How big is the column? How do you want your column packed? You want it very smooth and even and flat surface. Flat, okay? Stop right here. You want, follow my arrow. You want it flat. You want it smooth. You want it uniform, okay? You want an even distribution of everything at every point, okay? Okay, so tap pipette column to ensure a flat surface, okay? Then you use a ruler. And you want column about 2 to 3 centimeter. All right, now students, is it okay if I put 5 centimeter there? Is it okay for me to put 10 centimeter there? It is not. It is not okay. It takes forever for you to finish the experiment, okay? And as long as we're able to separate the compounds based on the polarity, you don't really want to increase the height, the column height too much, okay? So optional, you can add a little bit sand on top to protect the adsorbent. You want to protect it so when you introduce solution, it does not disturb. It does not cause the particles splatter, okay? So the TA decided to add a little more. All right, wet column using hexane. Is this the question I asked you in the quiz? Hello?
Yes.
Why is that? One more time. Why is that? You want a baseline nonpolar. You want the starting point nonpolar. Then you can increase the polarity of the column by introducing the solvent that is a little bit higher in polarity, okay? So this whole business of the column chromatography or TLC, thin layer chromatography, it is always polarity, polarity, and polarity, non-stop polarity, okay? It is only the polarity that makes difference, okay? All right, ensure that the column never run dry from this point on. Now students, can you help me understand why we don't want the column to run dry from this point on? If it runs dry, what may happen?
There could be cracks in the adsorbent.
You're saying if it is dry somewhere, then it creates cracks, and
So it could be uneven.
Could be uneven, you're right. Number one reason, yeah, crack is probably one of the possible reasons. The other possible reason is that when you lose the nonpolar solvent, then the polar adsorbent gets exposed again. Am I right? That polarity will be increased if the solvent is gone. Am I right? The particles, hey. Now students you're not able to understand because you probably didn't read the book carefully, okay? Let me go back. Share screen from my camera, okay? Are you able to see my document camera?
Yes.
Okay. So if this is the alumina particle, okay, when I add hexane, if I moisten it with hexane, I cover it and saturate the particle with hexane. Okay, and there will be some attraction coming from alumina, okay, indirectly. There will be some molecules of hexane covering the surface. Am I right? Okay, so when you have pigments coming, okay, and if the pigment itself is chlorophyll, okay, there is some attraction in between. Am I right? Indirect attraction. Am I right? And so the polar pigments and the alumina, there's some attraction in between. Okay, attraction. Okay. If hexane is not there and hexane is totally gone, okay, and you leave the column standing in the air for a while, guess what's going to happen? The water comes in right away. Understand? Then it will block the surface and will turn this whole particle dead. Did I tell you water is a killer? Understand? Okay, so you never allow the column to run dry because you don't want moisture to get in at any point and cause uneven polarity. Okay, let's say this area has moisture, this area has moisture. Then it's not even in attractive force around the particle. Am I right? This is the reason you can never allow the column to run dry because moisture can get in. Understand? Are you here?
I think so. Yeah.
Yes.
You think so? This is.
I think I understand. I know.
This is common sense to all chemists in the world. Okay, you can never allow the column to run dry because it will cause this adsorbent to change polarity spot to spot. It's uneven. Some areas still have hexane. Oh, then this area is more non-polar than the other side. You just don't want that because every particle should be the same, conditioned the same way with hexane only. Okay, this is the whole key. Okay, moistening the column evenly using hexane. All right, it is a very important common sense. Okay, extremely important. So it's a short, it looks like a very short statement here, but it's a very alarming warning right here, okay? And so hexane, nonstop hexane. More hexane if you want, okay? And you want this elution rate about 1 drop per second. 1 drop per second. Okay? All right. Hexane redissolve the pigment solution we call solvent-free extract. Once again, why do you want to redissolve it with hexane? Why not acetone? Hello? Why not? Because you want the same condition. The column right now is the hexane. So you want the solution here, also hexane base. They both have the same hexane solution. Am I right? The same hexane background. All right. All right, I want you to catch that golden moment, okay? When you introduce anything, any change to the column, you want to wait until the hexane and adsorbent meet at the surface. Allow the hexane level to decrease close to the decrease close to the edge of the sorbent level. Okay, you want these two surfaces meet each other when you introduce the green sauce, and you see that right away. Okay. All right, this is the time to add it. Yes, add the green. Gentle, very gentle. We introduce from the side of the wall. Okay, introduce the green extract at the moment when they meet. All right, you see separation right away. You see that? Sample, adsorb at the top of column. Right here. Right here. Okay? You see this pigment gets absorbed by the alumina particle. Aha, elute the sample with pure hexane. You add more hexane after the green solution adsorbed. And when the surface is saturated with the green pigments, the green solution of everything, you introduce hexane, okay? More hexane, a lot more hexane. It's dripping here. And we want you to note there's a movement of the orange band. Orange band. Tell me, what is orange band? What pigment group is that? Can you look at the lab manual? That was the structure of the pigments I show you. What is the orange band?
Keratin.
That's keratin. Simon, who said that?
Sam.
There was a couple of people who said it, I think.
Yeah.
Oh, then it's hard for me to reward you. Sorry. Let me keep going. Do you see, everybody, do you see the orange band is moving? Right here. This is the carotenoid. Keratin alpha, it all belongs to the same family, okay? It is the orange band. Or yellow, but golden. You see that? It is moving. Once again, tell me, which one is more polar? The green chlorophyll or the orange keratin?
The green chlorophyll.
The green chlorophyll is more polar, so does it move with hexane? So you're saying keratin is more nonpolar, am I right?
Yes.
Okay, so when you elute the column, when I say elute, it's like the same as washing. I wouldn't say washing. You are trying to introduce a nonpolar solvent for the keratin to dissolve and migrate with hexane. And why does it come down like this? Because it's gravity, am I right? It's gravity, right? Gravitational motion. Okay, so between the orange band and the green band, which moves first in this picture right here? Which one moves first? It's actually the orange band move first, okay? Because it is more nonpolar. So hexane can dissolve the nonpolar quickly and elute it out first. So what happened to the green, you may ask? Where's the green pigments? Where's the chlorophyll? Where is it? Right here. Doesn't want to move. Because the chlorophyll will say, I am polar, I'm not gonna dissolve in hexane, okay? So carotene, go ahead, you dissolve, you move, you migrate. I'm not moving. I am adhered, I am absorbed by alumina strongly. I am glued to the alumina particles stronger because I'm polar. Am I right? This is a conversation in between, okay? So why are you able to move the orange band, which is carotene, first? That is because carotene is nonpolar. It does not get attracted by the alumina. Alumina is polar. Are you all with me? Hello?
Yes.
This is the exact the exact principle I explained to you at the beginning of the class. Okay? Look at that. Is the yellow moving? Yeah, look. Look. Oh, I only want to collect the yellow. Or orange, sorry. When it comes down to color, it could be really subjective, okay? You can call it yellow, you can call it orange. It's carotene. So quick. 1 drop per second, roughly, okay? And the nonpolar pigments does not adhere to alumina much, okay? So it just migrate along with the hexane, no problem. I don't get attached to the adsorbent anyway. I get to move. Continue with 100% hexane until all the carotene out of the column. You separate carotene completely already. So what happened to the chlorophyll? It is still stuck in here at the top. You see how it goes now? Hello? To see is to believe. All right. Now the TA decided to move this green or whatever in between using hexane acetone, 90 to 10. Now tell me, compared to hexane, is this more polar or less polar? Is the 90-10 more or less polar? Hello?
More polar?
More.
Remember, acetone has carbonyl group, so it's more polar. Am I right? Okay. Let's see if the green does move along with it. Oh, it's saying, yeah, the green also start moving. Yeah. Okay. But let me ask you this. Does the green move fast or slow compared to the orange band? Hello? It's slower. It's moving much slower. Why? Why is the green pigments moving slower? Why is chlorophyll moving slower? Because all the time it is, I am a polar molecule. Of course, I get held down by the alumina. The polar alumina held me down, okay? You see the green is actually moving now, okay? Okay, you may see some color right here, but it's actually, it's a little bit grayish, okay? The camera itself is not 100% sometimes in terms of the color. Note the green band moves slower, okay? But it's moving. You see, the green was originally here at the surface. Now it's migrating slowly, okay? Continue. It's a slow one, so we got to be patient. So what was the eluent? What is the eluent here to move the green? Hello? Do you want to write it down? Take notes, okay? What was it?
9010 hexane acetone.
It is the 90-10, 90 hexane and 10% acetone. Okay? Thank you, Nathan. The green is moving slowly. It is still the 90-10. Slowly, it's moving. All right, moving. Finally, I can get you to move. Okay, guess what? Switch to 75-25. Oh, the TA is losing patience. I want to move faster. So I have to increase the polarity, am I right? Because like dissolve like. I want to increase it to 75-25. More acetone. Let's see if it works, okay? See? Yeah, you added more. 75-25. Oh, yeah. I want to switch the test tube so I can collect the green, only the green. All right, is it coming or not? Yes, it's coming. Oh, look at that. A little bit disturbance here at the top. Okay, yeah, some yellowish. Yeah, there's something yellowish. Yeah. Ooh, look at that. What's the color here?
Green.
It's green. Is it green to you? What's inside the green now?
Like
What?
a blue kind of thing on.
Is it carotene or chlorophyll? Hello? Is it?
I think it's still chlorophyll.
It's more chlorophyll. I can tell you, carotene is completely gone. Okay, so you see the green band collected completely. It's done. All right. The TA may probably add more 75-25, and yeah, that's the end. So was he able to separate the two groups, the orange and the green? Was he able to separate the two groups completely? The answer is, hey, what happened? Were you falling asleep? Was he able to collect the orange first?
Yes.
Then you collect the green. That means in the green juice, there was some portion of the orange already dissolved in there, but you know, our naked eyes don't see it, but the column can distinguish. You see how it goes? Okay. Now students, I will upload this whole video one more time, okay? I will upload it so you can view it as many times as you want, okay? This is all after. Remember this? It was the orange carotene collected first, okay? And then at the end, the more polar green collected. Am I right? It's actually more polar and it stick to the alumina tighter. And it moves slower. And it only moves when you apply a higher polarity eluent. Am I right? Are you all with me? Hello? Okay. Yeah. All right, now, ladies and gentlemen, today I will just stop here, okay? Because I want you to write down on the worksheets, okay? What happened, okay? I will upload the video one more time. You can write down the changes we made to the column. You want to digest it a little bit, okay? And next time, I want the worksheet turn in at the end of the lab, at the end of day 2. Are you with me? Are you with me? Hello?
Yes.
Okay.
Yes. Yes.
All right. Did you enjoy the video?
Yes.
Do you like it? It was really cool, okay? Actually, students rank This is probably either number 2 or their favorite, number 1 favorite. Really depends on the individual. But this is one of the favorite experiments. Okay, from students' standpoint, they really enjoy. Okay? Now, students, I want you to do this. Okay, official, no, I'm opening the wrong one. I want this one, sorry. I'm teaching 420. And this is my class right here. Okay? Students, everything you observe on the video today, you need to write down. Solvent you use to elute the yellow. Okay, get the RF value, determine, okay, this, I have a TLC plate already uploaded on the Beachboard, okay? You will determine the RF value later. Solvent used to elute the green band, okay? And I want you to answer questions, okay? This is due next time at the end, okay? And of course, I'll give you a little bit more warm up to correlate column chromatography with TLC, okay? Now remember from today, which pigment group adhere to the column tighter, stronger, and difficult to move? Which one is that?
Chlorophyll.
Is it chlorophyll? Very good, Amanda. Thank you. Okay, Amanda gets another point. All right, and I want all of you, okay, when you view the video again, I'll give you the link, okay? When you view the video again, it's my lecture video, okay? Go ahead and view it as many times as you want. And then answer the question here, and there will be some questions correlate TLC and the column chromatography together, okay? I want you to go back to this, okay? Want to show you the TLC results. Oh, by the way, I think I need to, pre-lab quiz, I need to turn off, okay? And I want to show you the TLC results, okay? After the green pigments and then the orange pigments, we call green band, orange band, or if there is in between fractions, we call fractions. In the test tube, we call fraction. If there is anything, then you see that in the TLC plate, okay? I want to share with you. This is from the students who were in my lab. Look at this, okay? The orange band that came out first, look how far it traveled. This is the pigments that was in chlorophyll. Hey, there is some yellow color. It is still the chlorophyll family, but it's yellow. It doesn't have the structure as carotene. It's not, but it's still chlorophyll family. Okay, it is just like in the fall season, you see, okay, the tree leaves turning yellow, turning orange. Why is that? It's because this pigment's predominant, okay? You may say, hey, the tree, do they have carotene? Oh, I don't know. If they turn color, most likely it's this family, okay? Go ahead and look up the word, the term in the book, okay? This is the original when it has the mixture of the two. Do you see how it lined up with each other? Okay, not much here. Okay, it's probably very low concentration, so you don't see that anymore. Okay, but do you see how beautiful it is? Okay, this is right after you get the green solution called extract. Yeah, we added that hexane, and to run the column, we save a couple drops and we run it on TLC, and then compare the orange band to carotene and the yellow. The yellow is right here. Then the chlorophyll family, okay? I want all of you download this and do the calculation of RF value, okay? It's already uploaded. And for today, I'm done. I'm done. And I want you to tell me, are you able to learn something today? Hello?
Yes.
Okay, to see is to believe. And I want all of you, okay, check my YouTube video again. Okay, I'll forward that. And please enjoy answering the question. And next time, at the end, you will have to turn in your worksheet. Are you with me? Might as well just do the question now when your memory is still fresh, okay? Because next time, you're supposed to turn in the worksheet at the end of the lab, and you will be a different person if I put you under pressure, okay? Might as well take your time and do it now, okay? Is that okay?
Sounds good.
Sounds good. And I will, okay, ask all of you to interact with me next time, okay? I encourage all of you, please, by all means, pick up your bonus point. Yes, every point you collect here is carrying the same equal weight as the final exam point. It carries the same weight, okay?